The next topic to discuss is the composition of linear transformations. If we apply two linear transformations in a row, for example. In this first line, we have an example. Here we start with t and then we apply s. With composition, we write backwards, t, and then assert s. This means apply t, then apply s. In general, composition is not commutative. This would not typically be equivalent to first applying s, then t. We also have identity transformations. So if we start in v, we apply the identity transformation of v, and then we apply t. We will write that as t circ iv, and this would be equivalent to just applying the transformation. If we were to do the identity transformation in w, we could say that t, then the identity transformation in w, is the same as just applying the transformation. If you apply the identity operator to a vector in its space, you'll get back the same vector. It does nothing. Lastly, we have associativity. This means if we apply t, then s, and then r, this is the same as doing t, and then s and r, as long as we don't change the order of these transformations. The inverse of a linear transformation is a special transformation. If t is an isomorphism, this means there exists t inverse. If the transformation goes from vector space v to w, where these are finite dimensional vector spaces, the inverse would take a vector in w back to v. It would be essentially doing nothing. It's undoing the transformation. If we were to first apply the transformation, then apply the inverse, we would end up back in our vector space v. This is equivalent to doing nothing. It's the same as applying the identity transformation in v. On the other hand, if we first apply the inverse, that's going from w to v, then we applied the transformation, we'll end up back in w. This is the same as the identity transformation in w. You may remember this sort of pattern from a matrix and its inverse. If we do a matrix times its inverse, we get back the identity matrix. Likewise, if we apply the inverse and then the matrix, we get the identity matrix. In order to check if a linear transformation has an inverse, we need to check if the matrix A is invertible, where A is the matrix of the transformation. This is true when the determinant is non-zero. A systematic way to find this inverse would be to write A and then the identity matrix, reduce it to the identity matrix on the left and A inverse on the right. This transformation goes from P2 to R3. Let's find the inverse. To begin, we could find the matrix of the transformation. This will be more obvious if we use isomorphisms in order to express a plus bx plus cx squared as a column vector. We can say it's isomorphic with R3, or we could write it as A, B, C. So if we have a 3 by 3 matrix multiplied by this column vector, how could we generate A minus C, 2B, A plus C? Now we've found a matrix of the transformation, and since the transformation can be represented by a matrix, we can say the transformation is linear. Let's first find the inverse using a matrix. Onto this matrix we add the identity matrix, and then we reduce. First we want a 0 under the first leading one, row 3 minus row 1, and we can just generate our second leading one, row 2 divided by 2. Next we can do row 3 divided by 2 in order to generate our final leading one. And lastly, row 1 plus row 3. Now we can clearly identify A inverse. We see that this transformation has an inverse. If it's not invertible, you wouldn't have the identity matrix on the left. So A inverse, we can even factor out the 1/2. T inverse goes from R3 to P2. To express our answer once again in this form, we can say the inverse of A, B, C. Since we've used the isomorphism, we'll have to convert back to P2, polynomials. What would this look like if we multiplied the inverse by ABC? We would get 1/2 A plus C, B minus A plus C. Now, using the isomorphism we established earlier, we can rewrite this as 1/2 times A plus C plus BX plus negative A plus C x squared. Here's another approach. We know that the transformation of a plus bx plus cx squared is a minus c to b a plus c. If we apply the inverse to both sides, what do we get? T, and then the inverse is just itself. And on the opposite side, let's write this with new variables, s, t, and u. We can equate these terms. We could either solve this system of equations by using a matrix or just substitution. Right away, we can find b. b is 1/2 t. We're looking for a, b, and c, expressed in terms of s, t, u. A equals s plus c. Well, let's find what c is. C is u minus a. Now we can plug that into our first equation. Now let's move the a to the opposite side. And to find a, of course, divide by 2. Now we can plug this back in to solve for c. 2u over 2 minus s minus u over 2. Now that we've found a, b, and c, we can sub those back in. So the inverse of STU is, as we can see, this is exactly the same answer that we got previously. So there are multiple ways of solving the same problem.